Okay. All right. Welcome back. I hope you had um, a good weekend, and I hope you have been able to get some practice using the problems on the chapter 12 problems that we discussed so far. Okay. A little bit of information about your midterm 2. Okay. Midterm 2 is on the 24th of this month, I believe. I think that's on Thursday. Um, you can always double check, but a few administrative issues, a few administrative points is that um, I made a few relaxations. Okay, I gave you a few. I made the midterm to a bit simpler. Okay, if you go to this, okay, first of all, raise your hand if you're able to see my screen. Okay, all right, good. Thank you. So here it is, 24th of June is when the midterm is scheduled to be. And the original plan was to have chapters 12, 13, and body plots as well included for the exam. But we are going to take body plots out. So for the exam, you just have to prepare for chapters 12 and 13. Okay. And in addition to that, let me make this very clear. On the 23rd, okay, on the 23rd, only homeworks 5, 6, 7, and 8 are due. So essentially, we are pushing this topic, body diagrams, body plots, to after the midterm. Okay, so I extended the deadline for homework 9 and homework 10 to the 7th of July. Okay, so on the 23rd of June, only 5, 6, 7, and 8 homeworks are due. Okay, and these correspond to chapters 12 and 13 in textbook. Okay, so when you work on these 4 homeworks, 5, 6, 7, and 8, you should be in good shape for the exam too. That's one thing. Okay, so no body plots, no time limit. Okay, the exam, I shuffled the exam a little bit. I modified a few questions, tweaked the questions, tweaked a few questions based on how the performance was in the previous midterm. So I don't think this would ever be a problem. Regardless, I took that time limit away, and then it's going to be available from 4 p.m. to midnight. Okay, so you can take 6 hours, 7 hours. You can take your time on the midterm exam too. So time is not a variable. That way, if you need to refer to a notebook, if you need to refer to some Google Notes or whatever it is that you want to refer to, you have the time. That's one thing. So that's about it. So today we will not be talking a lot of, we will not be talking about the midterm questions. I will probably finish up our discussion on chapters 12 and 13. Okay. Pratham says only homeworks 5, 6, 7, and 8. That is correct. Only homeworks 5, 6, 7, and 8 are due on the 23rd. That's the day after tomorrow. Other questions, please. What other questions do you have? Okay. So what did we do in the last class? What we did in the last class was to look at these Laplace transforms, right? We looked at integration by parts, the different techniques that we use to find the Laplace transform. You can use the definition, which is the integral definition of it, or you can use the tables 12.1, 12.2 to help us to pick Laplace transforms off the shelf and then use operational, functional, and definitions. Then we looked at examples. Okay, I showed you an example of how we can apply Laplace transform to make our circuit analysis easy. Okay, the main argument was the equation in time domain. It had a derivative term, okay, and it had an integral term. Okay, that's a complicated equation to solve. Whereas if you were to translate it into the Laplace or S domain using a Laplace transform, you'll see that your variable S, okay, you'll see that your variable, it's a polynomial, it's a quadratic equation in S, S to the 0, S to the 1, and S squared. Multiply the whole damn thing by S. But it's easy to see, right? If S were your variable, okay, and multiply the whole equation by S, you have S squared term here. You have S to the 0 term here, S to the 0 term on this side of the equation, and S to the 1 term here. So what you have is a quadratic equation or a polynomial equation, okay? A second order or a first order, a simpler equation to solve, okay? That is, I guess, the point I was trying to make in the last class was that when you solve, when you look at the output, well, that is going to appear as a variable S and some polynomial in S, okay? Or in other words, there is no integral and derivative terms in here. And then the analysis is much simpler in the S domain, okay, than it is in the time domain. In order to drive home that fact, I showed you an example. We took an example circuit, okay? And then we tried to analyze this guy, apply KCL at that node, okay, in the time domain. But instead of solving it in the time domain, we solved it in the frequency, in the S domain, okay? That's what we did in the last case. That's 12.6, applying the Laplace transform, okay? And I asked you to go over 12.7, inverse Laplace transforms, okay? The idea was, let me go back to my slides earlier, okay? The very last topic that I may have discussed is this guy. Does anybody remember what this is? I left you with a question, perhaps. Inverse Laplace. Correct. Ethan, thank you. The idea is we did all our solution in the S domain, and we expressed our output in the S domain in terms of some polynomial equation, okay? But the question is, how do you get back to the time domain, okay? Because time domain is what makes sense to the real world, and that's what the real signals are in, right? The S domain, the frequency domain, all of these are only for operational convenience, okay? The Laplace transform. So we have to get back to the time domain. How we get back to time domain is using the inverse Laplace transform, like Ethan mentioned. So this is where we left off in the last class. And that is where I left it as an exercise for you to go through and read up. Nevertheless, what I will do is I'll probably provide a very, very quick summary, okay, of the idea of inverse Laplace transforms. Okay, pay attention to this. So this is always going to be the format. Okay, the output function in the S domain is going to have a numerator and a denominator. Okay, if you don't trust me, let me go back to this. Okay, the problem that we solved in the last class. Okay, when we solved the problem in the last class, the output function in the S domain had a numerator and a denominator in S, which are variables in S. Okay, so the idea is we are going to develop generic tools in terms of going from the S domain back to time domain. Okay, so let me go back here again. So if you have a generic expression for your function f of s with a numerator and denominator, we are going to develop a few tools. Okay, you should have actually by now you should have practiced all of these techniques of partial fraction expansion. Okay, the first thing you want to remember is that the order of the numerator is n. This is a polynomial in s to the n. So this is nth order polynomial over m order. If n or m is greater than n, then we call it a proper fraction. And all our techniques that we develop apply to proper fractions. If not, all you have to do is to divide. Okay, divide using any number of tools. You can simply Google symbolic division when there are variables in S. Okay, Google can help you with that. If you do not have a proper fraction, if you have an improper fraction, then you have to divide the numerator by the denominator and then carry on with the techniques. Okay, so that's the idea of Laplace transform, which like I mentioned, you should have picked up by now. Okay, so I'm just going to give you some hints here and there. Okay, and this is the technique that you should have used when you have a proper fraction. The value of n here is 1. That's the highest power of s in the numerator. In the denominator, the m, the highest power of s is 3, or it's 4 actually. Okay, it's 4. Okay, then you can use your partial fraction expansion when it is proper fraction. It's a proper fraction, so we can use our partial fractions method. Okay, in order to find the variables, not the variables, the values for a, b, c, and d. Okay, using this cover-up method that's detailed by Oliver Heaviside. Okay, this is the idea of partial fraction expansion. What you want to understand is the equation on the polynomial on the left-hand side and the one on the right-hand side are equivalent. Okay, they're equivalent. It's just that it's a straightforward, easier method to get from here to here. Okay, it's a method to get from the left to right. Why do we care? The reason is simple, because if you express your function as a partial fractions, okay, then going from here to the time domain is easy. Okay, so in other words, what you do is each partial fraction has one term in the time domain. Okay, so as you can see, each partial fraction has one term in the time domain. They're color coded here. Okay. Okay, so if your overall transfer function has 4 partial products, then applying the inverse Laplace transform, you get 4 terms in the time domain. Okay, so I'm not elaborating on this. I'm just providing you some hints. Okay, because this is something you should have practiced, like I mentioned towards the end of the last class. Okay, so 12.7 inverse Laplace transforms. Professor Russ Tetro's videos should provide you some examples as well. Okay. The other thing that you want to remember is when you're looking at the solutions for the denominator. Okay, when you're looking at the solutions for the denominator, there can be 4 kinds of roots for the polynomial in the denominator. Okay, the roots of the denominator can be real and distinct. Okay, and the roots of the denominator could be real and repeated. Okay, real and repeated, and then the roots could be complex. Okay, the roots could be complex and distinct, or the roots could be complex and repeated. Okay, let's see. So here is an example. Now, when you're solving this example, I'm not going to go over this elaborately because Professor Tetro does that. What I will mention though is that here the order is the order of the numerator is 2 and the order of the denominator is 2 as well. Okay, therefore it's not a proper fraction. Then what you want to do is to divide the numerator by the denominator. Okay, and then leave that alone, and the rest is going to be it's going to be a proper fraction that you can use your partial fraction expansion to. Okay, if you did not already practice this, well, you should practice this part. Okay, so look at Russ Tetro's videos. Look at the example that he talks about this very example elaborately. Look at that. Okay, so what you want to remember is, even as you are solving all of this seemingly complicated math, it's not really complicated. It's straightforward. If you understand that all of this is meant to make our life easy, believe it or not. Okay, this partial fraction expansion makes circuit analysis easy, extremely easy in the S domain compared to what we would have had to do in the frequency domain, in the time domain. Okay. Now, did anybody practice, look at some problems here and there in the partial fraction expansion? Anybody tried the homework problems? Nobody tried the homework problems so far? Okay. Okay. So I strongly advise you to look at those homework problems if you did not already. Okay. Look at Tetro's videos. He talks about these examples. Okay, so maybe I can do some problems tomorrow. I had a bunch of, I worked on a bunch of problems. Okay, in terms of how to solve this, the initial value theorem or final value theorem, all of those, I can go into the details of how to get from this form into a partial fraction expansion form. Okay, how do you find the value of K1, K2, and K3? And from there, how do you get to the time domain? Okay, it's this process is it's better practiced. Okay, and then once you work on some homework problems and you have questions, that would be a good time for me to um, add um, to any gaps that you may have in your preparation. Okay. All right. So there is a method to this madness. If you think about it, if that's your S domain expression, okay, then the corresponding time domain expression is going to have a relationship. Okay, a delta, a constant in free S domain is going to give you a delta. A 3 here, 3s plus 2 would give an equivalent of negative 3 e to the negative 2t, because there's that negative 3 over there. Okay, and then if you were to look at this guy, 2 by s plus 4, the transform of that, the Laplace transform of that would be 2 e to the negative 4. Okay, so that's the partial fraction expansion and inverse Laplace transform into the time domain. Okay. Now, the only thing that you want to remember is this guy. If your polynomial in the denominator has complex roots, then complex roots always appear as complex conjugate pairs. Okay, that's something you want to remember. Okay, if there is negative 5 plus j12 as one root, then negative 5 minus j. First of all, you know complex conjugates, right? X plus jy and x minus jy. They're complex conjugates of one another, right? So if x plus jy is the root of a quadratic equation in a realizable circuit, then the other root would be its complex conjugate. Okay, so there are certain certain rules of thumb that we can apply here. Okay, if the roots of this equation are complex conjugate, is one root is a complex number, then the other root would be its complex conjugate. Okay, but here is a question for you. Okay, how do you know? Okay, how do you know? For example, this guy, s squared plus 10s plus 169. For this polynomial quadratic equation, how do you find the roots? How do you find the roots here? Factor. Can you elaborate? Alistair, how do you mean? Probably complete the square. Sure, there are many methods to find the root, but here is one technique. Sure, there are many methods to find. Using completing the square is one method, but here is ax squared plus bx plus c. Okay, if you had an equation that looks like this, the roots of this equation are given by this formula minus b plus square root of b squared minus 4ac by 2a is one root. Negative square root of b squared minus 4ac by 2a is the other root. Okay. Alternatively, you can use MATLAB, you can use Google to find the roots. But here, let's try to find this guy, find the roots of this guy, and see if that is what we get from the problem or not. In this case, b equals to 10, a equals to 1, so ax squared plus bx plus c, and c equals to 169. All right. So if I were to, is that the equation? 169 s squared. Yeah. So if I try to find the roots of this guy, minus b, the roots are plus or minus b squared minus 4 times a times c by 2 times a. A is 1. All right. So how much ever that comes out to be, 169 times 4, 100 minus that. Could somebody give me the expression for that? Plus or minus square root of 100 minus. What's this value? $676. Okay. Okay. So minus, so this comes out to be minus 10 plus or minus square root of negative 576 by 2. Okay. So that's going to come out to be negative 5 plus or minus j. Square root of 576 is 24, I think. 24 by 2 is 12. So one root is negative 5 plus j12, and the other root is negative 5 minus j12. That is what this formula would tell me the roots of this equation are. Okay, and if we go back, sure enough, one root is negative 5, negative j12. Okay, and the other is its complex conjugate, negative 5 minus j12. Okay, s plus a equals to 0, s equals to negative a. Okay, so negative a. That's one of the roots there. Okay, so if you have a quadratic polynomial, a squared polynomial, a polynomial with quadratic, you can easily find the roots of this guy. And if you have a complex pair, okay, minus 5 plus j12, minus 5 minus j12, that procedure, minus b plus or minus, will give you those roots. Okay, once you have those roots, well, from there, it's straightforward. What you have is you find the value of a, b, and that's it. You don't have to worry about finding the value of b star or the complex conjugate, because once you know b, b star is just the other angle, 4.1667 angle 90 degrees. That would be your complex conjugate. Okay, once you have that, so once you have k theta by s plus alpha minus j beta form, okay, once you simplify, okay, this is A, this is B, and this is B star. Okay, once you do that, so we are talking about a scenario where the roots are complex, and then they're coming in conjugate pairs, okay, and then they are distinct. Okay, once you have that, once you know the value of k, okay, once you know the value of k, you should be able to use table 12.3. Okay, table 12.3 shows you how to get from this form into the time domain form. Okay, when the roots are complex and distinct. So what are we doing right now? We are looking at partial fraction expansion, or in other words, if I had a V out of S, that's a polynomial. I don't know, I just made these numbers up. How do you get from here into the time domain? Okay, this is where we would do the partial fraction expansion method. Okay, A by the root, B by root, C by the root. Okay, the roots of the denominator are expressed as the partial fraction. Then you solve for it. These partial fractions are expressed such that it's easy to go from each of the partial product into partial fraction into the time domain. Okay, and then we are looking at the particular case of complex roots when the denominator has complex roots and they're distinct. How do you get from how do you apply the inverse Laplace transform? Okay. Questions, please. So like I mentioned again, you have to read through this. When you're looking at you can use MATLAB or Google, of course, to find these roots. Okay, you can use Google or MATLAB to find these roots. But what I was about to say is that partial fraction expansion, when you're trying to do that, the roots of the denominator, okay, denominator roots, they can be real or they can be complex. Okay, real roots could be repeated or distinct. Okay, the exact same thing for complex roots as well. Okay, so the roots of the denominator polynomial could be real or they could be complex, and then you have techniques to go from the partial fractions into the time domain form. Okay. Questions, please. Questions so far. Okay. Please bear with me for a little bit of time. We'll get to more and more interesting stuff. Okay. Now let's talk about poles and zeros. I'll cut the crap. I, the simple idea is if the numerator is a polynomial and the denominator is a polynomial, okay, all the roots of the numerator are called zeros. All the roots of the denominator are called poles. Okay, that's all there is to it. And you can plot them on the x-axis and y-axis. Okay, if you had an a polynomial that looks like this. Okay, if you had a polynomial that looks like this, and you're asked to plot the poles and zeros, don't be thrown off. Okay, divide and conquer is the attack strategy that we will use. Let's look at the numerator. The numerator has 1, 2, 3 factors. Okay, so s equals to -5 is one root of the numerator. Okay, then s equals to the negative of this guy. Okay, s equals to -3 plus j4. If you were to plug in this value here, all of the numerator turns out to be 0. All right, so that's the idea of 0. Okay, the other 0 here is this guy, s equals to -3 -j4. Okay, so there are 3 solutions here. There are 3 zeros for the numerator. Hence, starting with this guy, you put a 0 at -5. So this is your real and imaginary axis, right? There's a real plane and there's an imaginary axis. Okay, J, when you have your real, this was what we were doing for the x plus jy form, right? The real axis and the imaginary axis. Okay, real axis and the imaginary axis. S equals to -5 is a 0. Okay, because that's the factor of the numerator, one of the factors of the numerator. Hence, corresponding to that, you place a 0. Okay, you annotate it using a 0 because that's the real part, x equals to, or the real part, s equals to -5. Okay, how about this guy? -3 plus j4 is one of the roots of the numerator. -3 plus j4, that's plotted as a 0. Okay, similarly, its complex conjugate, okay, -3 minus j4. Sure enough, it's right here, -3 minus j4. Okay, that's a 0. So all the roots are all the factors of the numerator polynomial are identified as zeros, and the other ones, okay, the roots of the denominator are identified as x, or poles. Okay, they're identified as pole. Okay, one pole is this guy, s equals to -10. Okay, s equals to -6 plus j8 is the other root. So -6 plus j8 is one root, and -6 minus j8 is the other root of the denominator, which is a pole. Okay, so the bottom line is simple. Don't be thrown off by the idea of poles and zeros. Okay, The only thing you want to remember is if there's a factor in the numerator, it's called a zero. If you look at the denominator, the factors of the denominator are called as poles. Okay? S equals to 0, for example, I forgot, is a pole. Okay? At origin. So, in effect, in summary, poles are nothing but the roots of the polynomial in the denominator, while zeros are the roots of the numerator polynomial. Questions? That's the idea of poles and zeros. Okay. If you have any generic term, okay. So here, P1, negative P1 is a pole, P2 is a root, negative P2 is a pole. Similarly, you get the idea, right? PM, negative PM is a pole. Okay, and then there are zeros. Okay, the idea of initial and final value theorems. This can be used as not only a quick sanity check, but also to find the initial conditions, the initial values of the functions in the S domain. Okay, simply, if you want to find the initial value, initial value of this function in the time domain, as t tends to 0 plus, okay, as the time is very, very, very close to the initial condition, 0 time, then what you want to do is you can find f of s, multiply that by s, and find out the limit as s tends to infinity. Remember, one is in the time domain and the other is in the frequency domain, right? Naturally, there is a reciprocal relationship between the two, right? So it's more or less reasonable to expect that this relationship bears out. When you want to find the initial value in the time domain, you want to look at s times f of s and see what its value tends to as s tends to infinity. Okay. Similarly, if you want to find out the final value in time domain, that's what we are looking at, right? A function, what is its value as time tends to infinity after a very, very long time? Then what you want to do is you want to look at its Laplace transform, multiply that by s, and investigate how this function behaves as s tends to 0. Okay, so the only thing that you want to remember is, and you'll see problems like this on the midterm, problems like this on the homework, so on and so forth. Initial value can be found out by setting the value of s to be infinity, s in s times f of s, while the final value in the time domain can be found out by setting the value of s to 0 in this function s times f of s. Okay, and then there are, of course, there are some assumptions that you have to pay attention to. And I remember there is one question corresponding to this on the homework. Okay, can you apply an initial and final value theorem under so and so and so condition? Okay, if you see questions of that sort on the homework, can you apply initial or final value theorem? Well, you want to make sure that these conditions are met. Okay, all the poles of f of t lie in the left hand plane. Okay, you don't want any poles on the right hand plane. See, if I go back, that is the left hand plane, that's the right half plane, right? And see, this pole and this pole and this pole are all lying on the left hand plane. Okay, that is what you want. Okay, that is where you can apply your final value theorem. Okay, and of course the initial and final value theorems can be applied under certain conditions. Okay, a non-repeated pole of f of t may exist at origin. Okay, so that's exactly what happens here. You see, there's a pole at origin, right? A non-repeating pole at origin, and the rest of the poles are all on the left half plane. So this function is a good candidate for applying initial and final values. Okay, and you want to understand the strengths and limitations of the final values. Okay, so the lecture by Professor Tato talks about applying the initial value theorem and then also the final value theorem. Okay, some examples. Go through his lecture to understand the initial and final value examples. Okay, let's see what else. So that completes our chapter 12. Okay, the most computationally nagging aspect is this guy, finding the partial fractions expansion. How do you go, especially when you get to a point where there is repeating roots? Okay, um, they could be real or they could be complex. When you have repeating roots, how do you find these values, coefficient values? So you have to practice them for you to even face those problems to the point where I can walk you through any problems that you may have. Okay, so that's about chapter 12, applying Laplace transform in circuit analysis. Okay, and more about Laplace transform itself. Any point along the vertical axis is valid and does not violate the requirements. No, it only has to be at origin or the left half plane. Origin is okay, but not along the y-axis. That's okay. That's not okay. Okay. Other questions, please. Okay, so that's the idea of initial final value theorems, and chapter 13 is what is next on our discussion. Let's see. Okay, so chapter 13 is about using Laplace transform to perform circuit analysis. Okay, if you remember the frequency domain analysis where you were doing j omega, okay, j omega was your unknown variable. Omega was the j omega was the term that we were using frequently, right, to calculate the impedance at that particular omega frequency. Okay. Similarly, we are going to do similar transform Laplace application to circuit analysis. Okay. But before we move on to chapter 13, do you guys have some questions? What questions do you have? I know one of you has a question about homework. What problem was that? Pratham, did you have a question? Pratham has a question and wants to share the screen. Let's see if I can, Pratham, make you the Pratham, make a co-host. Stop my screen share. You're welcome to share your screen. Pratham, do you have a particular question about this?
Yes, Professor. So I did the KCL for these two points, right?
Okay.
And then I got an expression which was in terms of constants, RC and IDC and S, but that was not really matching with the given answer right here.
It was not matching with any of these answers.
Yes, correct.
Is that what you're telling me? Okay.
Yeah.
Now this is so what I'm going to do is to let me do this. Why don't I start sharing my screen, and then just give me a second so I can take a screenshot. Okay, of your screen. Okay, let me start sharing my screen. Pratham. Okay, so this is a chapter on Laplace transforms. So I'm going to paste the image here. Did we solve this problem in the class at all?
We solved something similar to it.
Something similar, not exactly the same. Okay, okay, I see. Let's see. Thanks, Pratham, for this question. Cancel. Okay. Okay. So let me see if I can drag this further down. The question is to find the Laplace transform of the output current I of S. Okay, and this is what we want to remember. Here is the Laplace transform is all shown in capital capital case. Okay, lowercase letters usually represent time domain. Okay, lowercase letters usually represent time domain. Pratham has this question. Do you want to get us started, Pratham, on how you started approaching this problem at all, or do you want me to take it from the top?
So we can use KCL for starting it.
Using KCL, right?
Yeah.
So,
Okay.
so there's only one node. What we want to remember is this and this. They're just one node, right? So let's call this node as one. Node 1, KCL at node 1, right? So if we look at the currents, there's one current over there. Okay, there's another current, 3 and 4 currents. You see, there are 4 currents here. One current is through the IDC, or let's write that KCL at node 1, negative IDC plus the current in the inductor IL, okay, plus the current in the resistor IR, plus the current in the capacitance IC, which the problem wants to call this as I0. Okay, I0. We can call it as IC. I simply annotate that I0 is IC. All of that should be 0. Right? Now the value of IR is relatively easy to figure out. IR, what would be IR? Let's
V
write
naught
it all
divided
in
by R.
IR equals to V naught over R. Is that what I heard you say, Pratham?
Yes.
Right. So let me be careful here. I'm going to annotate all of this in the lowercase, meaning that it's all time domain. IC, IDC. Okay. So this is all lowercase I, lowercase I. Okay. And what would be the IL? What would be the expression for IL? Anybody can give me the expression for IL? Remember the current in the inductor. Maybe I can, if I make it a little better, cleaner, you can tell me the expression for IL. That's the current flowing through the inductor, IL. Okay. VL equals to LDI by dt. Right. So if I were to find IL, then that would be 1 over L integral 0 to t V naught of t. Okay, that's V naught, right? At node 1, this is V naught, right? Everybody with me so far? Now, what would be IC? The current in the capacitance. IC
C
equals to,
times dV over dt. C times dV over dt.
thank you.
dV naught.
That's, yeah. You're right, C times dV naught over dt. So if I were to plug each of these terms in, so I know IR, I can plug it in here, okay? I know IC, I can plug that value in there, okay? And then of course I can, what else? IL, well, I know that value from here, this expression. So I should be able to set up this equation, okay? Once I set up this equation, it's going to come out to be IDC equals to IL plus IR plus IC, all right? So now IDC equals to 1 over L integral 0 to T V naught of T plus V naught of R for IR plus C D V naught by dt, right? Present?
Yes.
So is this your question, or did you encounter a problem further on?
So I wasn't really able to solve from here.
You are able to solve, or you want me to take you a couple of steps?
No, you can do it from here. That would be better.
You can take it from here, right?
Actually, you can do it from here. That would be like slightly better.
I think your voice is breaking up. Can you say that again?
Oh.
Continue the problem. Okay, I see it. Okay. Can you continue the problem here? Okay, yeah, I can continue the problem here. Let's see. So we are here. Okay, so what we are going to do is to solve this problem in the time domain is pretty bothersome. Okay, there's an integral term, there's a derivative term. We have to solving in derivatives and integrals is painful. So what we do is to convert everything into Laplace domain. Apply Laplace transform. Okay, we apply the Laplace transform. So Laplace transform of IDC U of t. Okay, IDC U of t. This is, let's be careful because that's turning on. Remember, the first class on Laplace transforms was about switch that is turning on and off, step response. Okay, something is turning on that has a U of t. Okay, now when we are applying the Laplace transform, okay, the Laplace transform of the left-hand side is the Laplace transform. So that's the Laplace transform of 1 over L integral 0 to T V naught of T plus the Laplace transform of V naught over R plus the Laplace transform of C dV naught over dt. Okay, so there are three terms here. There's one term, that's this guy, after taking the Laplace transform. Okay, then there is this C dV dt term. That's right here. Okay. Then of course there is this guy. Which is shown here. 3 terms. And the left-hand side is that guy. Okay. Everybody with me so far? So all I have done is simply apply the Laplace transform. I did not even apply the Laplace transform so far. I simply annotated each term and showed that I want to apply the Laplace transform. Okay. First things first. Let's see if we can do this guy. The Laplace transform of a function, some constant times u of t, the Laplace transform of it is that constant over s. Okay, don't trust me, you can go back to the tables that I may have copied here earlier, wherever that is. There it is. Okay, if you have u of t, the Laplace transform of that is 1 over s. Okay, a constant multiplied by that is not going to change a thing. Okay, so that's exactly what I'm doing. U of t is what I have. Okay, u of t will give me 1 over s. Okay, and IDC will give me IDC because it's a constant DC value. Okay, so the Laplace transform of this guy is I over DC. The Laplace transform of 1 over L integral 0 to t v naught t, okay, dt. That guy would be, what do you think the value of the Laplace transform would be here? What would be the answer here? If I were to look at the Laplace transform of this guy. Any volunteers? What do you think the answer would be? If all I'm doing is looking at this term, the Laplace transform, what's the Laplace transform of that term? Mahavir, Martin, Natalia. Refer to table 12.2. Okay, refer to table 12.2. Pratham says s times f of s. Let's see if that is the case or not. Somewhere in here, I must have copied this table 12.2. Okay. If I have a function, then and the integral of that function, then the Laplace transform of this compound operation is the Laplace transform of the function itself divided by s. Right? So that is what we are going to do. Okay. Here, I'm going to write 1 over L as is because that's the constant. But then I have the Laplace transform of a function, which is the same as the integral of a function. When I want to do the Laplace transform of it, that would be the same as the Laplace transform of a function divided by s. So v of s divided by s. would be the Laplace transform here. That's from table 12.2. Okay. Okay. Yeah. All right, Pratham. Now the same thing for the Laplace transform. So that's the Laplace transform of the one term. The next term is the Laplace transform of V naught over R, which is going to be the same as V naught of S over R. Okay, that is not going to change the Laplace transform. So this term, highlighted in yellow, is the Laplace transform of the resistor. Okay, then the Laplace transform of the derivative C dV naught of T by dt. Okay, that's for the capacitor. What's that value? If I have a derivative of a function, okay, if I have a derivative of a function, S times f of s minus the initial condition. This is where we can use our initial value theorem, okay? But now we don't need it because the initial conditions are given to be 0. There is no energy stored initially is the given part of the problem. So S times f of s minus f of 0 is going to come out to S times f of s, okay? Because the initial conditions are 0. So here we have C times V naught of S times S, okay? So we can, yes, thank you, Pratham, okay? So we can gather all the terms here. So on one side, I have IDC over S, okay? IDC over S is the sum of the three terms here, okay? Sum of the three terms, 1 over L, V naught of S over S, plus V naught of S over R, plus C times S times V naught of S. Okay, so from here, so this is your equation. So if you think about it, and if you multiply the whole thing by S, IDC equals to 1 over L V naught of S plus V naught of S times S by R plus C S squared times V naught of S. So it's a polynomial in S squared, AX squared plus BX plus C format, okay? A, B, and then C format. Okay, from here, you should be able to calculate any variable that you want to calculate. Okay, if you want to calculate V out, jolly well, you can do that. If you want to calculate I out, well, if you know V out, then that will be V out over ZC. Okay, so once you know the voltage across the capacitance and the impedance of the capacitance, then finding the current is straightforward, right? Questions, please. Okay. So if you want to calculate I0, the textbook or the homework problem asks you to calculate I0, right? So this is the I0 component. Remember, this is the I0 component. This is the IR component. This is the IL component. All of that equals to the IDC in the time domain. Okay. So if you add up in the time domain, that should equal the KCL holds true there. Pratham, did that answer your question, or did you have further questions about that? For getting an equation between VO of S and IO of S, use the capacitor equation, right? Right? So in order to get the current equation, all you have to do is this guy, okay? The current I0, that's the current in the capacitance. That's the current in the capacitance. That is VO, which is the voltage across the capacitor, by 1 over SC. Okay, that's the impedance of the capacitance. So it will come out to be SC times VO. Okay, so you can get a value for VO, not a value, an expression for VO from this equation. Once you have that, you should be able to calculate the current division. Okay, good question. Okay, getting V0 is straightforward. Getting I0 from V0 is just a matter of the voltage across that capacitance divided by its impedance. Okay, other questions, please. What other questions do you have? Okay. So what we have done so far is to complete chapter 12. Okay, let me go back to my schedule if I have it on me at all. Okay, do I have the schedule on me? Course syllabus and link in a new tab. Okay, today we are supposed to have started on circuit elements and applications in the S domain and the transfer function and steady state response. But that's not a big deal. We're just about a day or two behind. It's easy to catch up, okay? But so far, we are done with poles and zeros, initial and final value theorem, okay? I want to stop there, okay? I want to stop there for today. Tomorrow, when we come back, I'll give you more hints about the exam, and I'll finish up chapter 13 tomorrow, and then we'll postpone body plots to a later time. Okay, I'll give you a very straightforward, very easy, simple method to look at body plots. Okay, 10 times below the frequency, at the frequency, 10 times above the frequency. Fun stuff when it comes to body plots. So I'm confident that by postponing body plots to a later time, we are not going to suffer a lot later on. We are not postponing a lot of pain. But the important thing is, I want to make sure that we are only focusing on topics that we need for the midterm. Okay? So that said, the class notes, including all of this, annotations, should be backed up to Google Drive in a minute or so. in less than a minute. But before we end for the day, any questions? What questions do you have? So what Pratham did today is a good thing. He brought some questions to the class. He worked on the homework and brought some questions to the class. That way, I'm able to work on example problems on something that you may have a hard time with. Okay. And he, of course, he was nice enough to let me know ahead of time so I can budget some time in today's class for the problem. So if you work on some homework problems, including chapter 13, okay, you are welcome to go ahead and watch Professor Tetro's videos and get started on homeworks corresponding to chapter 13 and 12, okay? And then you can bring me those problems tomorrow. Bring those problems tomorrow, and then we'll look at some examples that you want to look at. And then I'll also throw some hints about the final exam, okay?